Hey everyone, and welcome. Today we're diving into a really interesting problem called maximum number of events that can be attended to. We'll break down the logic step by step, from the initial idea to a fully optimized solution. Let's get started. So here's the deal. We get a list of events. Each event has a start day, an end day, and a value you get for attending. We're also given an integer, let's call it k, which is the maximum number of events we're allowed to attend. The key rule is, you can't attend two events that overlap in time. Our mission is to pick a set of events that maximizes our total value, without breaking any rules. Let's walk through an example. First things first, it's almost always a good idea to sort the events by their start time. It just makes things easier to reason about. Okay, so we have 3 events, and we can attend at most 2. Let's consider our first event, event A. What if we decide to attend it? We get 4 points, and it finishes at the end of day 2. Now, can we attend event B? Nope, it starts on day 2, which is an overlap. But we can attend event C, since it starts on day 3, so attending A and C gives us a total value of 7. What if we had skipped event A? Then we could attend event B for 1 point. It ends on day 3. Can we attend C? No, because it starts on the same day, so that path gives us a value of only 1. Clearly 7 is our answer. This attend it or skip it decision at each step is a huge hint that we can use dynamic programming. So let's formalize that attend or skip idea. We can define a function, let's call it dp-, that takes 2 arguments: the index of the event we are currently considering, and the number of events we can still attend. At every single event we face a choice. First, we can just skip it. If we do that, our potential score is whatever we can get from the rest of the list, starting from the very next event. The second choice is to attend the current event. If we do, we get its value. But then we have to find the best we can do with 1 less ticket, starting from the next event that doesn't overlap. Our function will simply return the better of these 2 options. Now that raises a question. How do we efficiently find that next non-overlapping event? Remember, we sorted everything by start time. So if we attend the event at index I, which has some end day, we just need to look in the rest of the list for the very first event, whose start day is greater than our current event's end day. Because the list is sorted, this is a perfect job for binary search. It's much faster than checking every single remaining event one by one. And here's what that looks like in Python. First we sort the events. That LRU_cache you see is a handy decorator that automatically handles memoization for us, which means it saves the results of our DP function, so we never compute the same state twice. Inside the function, we have our base cases. If we're out of tickets or out of events, we return 0. Then, we use bisect_left, Python's built-in binary search, to find the index of that next valid event. Finally, we return the maximum of our 2 choices. Either attend the current event, which means adding its value and calling DP for the next valid index with 1 less ticket, or skip the current event and just call DP on the next index with the same number of tickets. This approach is good, but we can make it even better. Think about it. For any specific event, say event 5, the next non-overlapping event will always be the same. Our current code does a binary search to find that same result over and over again. So the optimization is simple. Let's do all the binary searches just once, at the very beginning. We can create a new array, maybe call it next indices, that stores the result for every single event. It's a classic time-space trade-off. We use a bit more memory to make our main logic much faster. The code for this optimized approach looks very similar. You can see the new part at the top, a loop that goes through each event, does the binary search, and appends the result to our next indices list. Then, down in our DP function, the line where we find the next event is much simpler. Instead of a binary search call, it's just a fast lookup in our pre-computed array. This small change makes a real difference. So let's compare their performance. The first approach involves sorting, which is big O of n log n. Then, the dynamic programming part had n times k states, and each one performed a log n binary search. In our optimized version, the pre-computation step takes n log n time. But once that's done, our main DP function only has n times k states, and each one is now a constant time operation. This means we've effectively removed that log n factor from the most expensive part of the algorithm, which is a huge win. For space, both need about n times k for the memoization cache. So to wrap it all up, when you see a problem about making a sequence of optimal choices, dynamic programming should pop into your head. Sorting the input first can often simplify the problem immensely, and if you find yourself doing the same search or calculation over and over inside a loop or recursion, ask yourself, can I just compute this once beforehand? That's the core idea behind pre-computation, and it's a super powerful tool in your coding toolkit. Hope that breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. And hey, if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.